Okay. So let me explain what I just gave to you all. So the purple sheet is assignment 4-1. That's what I'm going to go over that information tomorrow. So that's the assignment for tomorrow, which is going to be due on Wednesday. On that purple sheet, I do not want that scanned back to me. Do not answer a single thing on that purple sheet. All that is do is providing information. Okay? Do not send that picture. I do not want it back. Do not write a single answer on that sheet. On a deal like that, here's your sheet of paper. And I want that line drawn like this. I want the answers here. I want the work over here. Okay, I cannot emphasize this enough. Do not write. I do not want to see that purple sheet again. Okay, you're going to put everything on another sheet of paper. Then there's a sheet of lecture notes about net forces. Okay, that's what I'm going to discuss on a lecture that I'm going to send out to you on Wednesday. Okay, and then that net force follies is what I'm going to give you Wednesday, which is going to be due on Thursday. Okay, so here's the sequence for the week. So tomorrow, the lab that you all are going to finish today is due tomorrow. Tomorrow, I'm going to introduce the stuff for the net forces sheet, which is the purple sheet, which is going to be due on Wednesday. And then Wednesday, I'm going to send out the lecture on net forces. So that assignment is going to be due on Thursday. So that way, I've kind of got a plan way far in advance with you guys, since I won't see you all again until Thursday. So that's kind of the sequence. So if you want to write that down, I've got it up there. I'm going to send you that in an email so you can kind of begin to plan that. Okay. So let's talk about beginnings of lab, which your compatriot started on Friday. Okay. And here's what they did, and if you guys want to if you guys would actually have time, if you guys, and I would recommend that you kind of begin to do this. So what they did is they began an investigation into what's called the coefficient of friction. So on your equation sheet, you have this equation that forced friction equals mu times force normal, and it's an absolute value. So what they did at the beginning of the lab is that they were trying to calculate mu. So if you solve for mu is force friction over force normal. This is the Greek letter mu. It also is usually referred to as the coefficient of friction. Okay? Means the same thing. There's a couple of things about mu. Mu, there's three things you need to remember. First off, it has no units. Okay? And the reason that it has no units is because to calculate mu, you're dividing newtons by newtons. Okay? So mu is one of the very few instances where it's just a number. Okay? It has no units. This is still an absolute value thing. So mu is never a negative number. Okay? All right? It's an absolute value. All it is a ratio. That's it. And the third thing, mu is rarely greater than or equal to 1. If you ever calculate mu and you get like 5 or 12 or 8, even if you get a coefficient of friction of 2, you did it wrong. Okay? Mu is almost, at most, it might be 1. Okay? Maybe a little bit over that. But certainly not a big number. So if you ever get a big number from mu, you've done something wrong. Okay? Now, here's what your cohorts did at the beginning of lab. So you got a block of wood. Now, and you got to get used to the terminology. In the physics class, when I'm talking about the weight of the block, that's a measure of the gravitational pull. Okay? And that's going to be in newtons. So when I ask for what does something weigh, I don't want an answer in pounds. I don't want an answer in kilograms. What I'm talking about is the gravitational attraction between an object and this big strange rock that we're on. Okay? So get out of your minds now, weight is in pounds, it's not in kilograms. Weight and gravitational force mean the same thing. It's going to be in newtons. Now, there's two ways that you can determine the weight of an object, okay? One option is that you use a scale, and the other one, you use this at Fg equals mg. So, we've got these handy dandy little Newton scales, okay? If they would turn on, that would help. There we go. And we're going to use these a lot. So, one option is that you just take this, and one of the things you always have to do is re-zero this scale in however direction you're going to use it. So I'm going to hold this vertically, so I'm going to re-zero that. And then I'm just going to take this block and lift it up. And it's like 3.82 newtons. So one of the things that I can do, it's very simple. You just take the scale, you hook it up, you get a number, boom, you're done. Okay, there's no calculations to do. This is it. So this would be 3.82 newtons. Now, it's always the debate is that, do I make this positive or negative? If all I'm asking you is what something weighs, just give me the number, okay? Now, if you're talking about drawing it as like a vector quantity where you're going to make all the forces add up to equal to 0, then you can make it negative. Now, if you don't want to think, it's like, I don't want to worry about it's positive or negative, you can just always make it negative if you want, okay? It's up to you. But one thing about this is that this number changes depending upon where you are in the universe. So if I take this same block of wood and I'm on the moon, it's going to weigh a lot less because of the fact that there's less of a gravitational attraction between this block and if I was on the moon. If I could go to Jupiter, I'm sure I can't stand on Jupiter because it's a gaseous planet, but if you could, this thing would weigh a lot more because gravity on the surface of Jupiter would be a lot stronger. So weight changes depending upon where you are in the universe. Mass, which is just a measure of how much stuff there is, doesn't change. So if I take this block of wood to the moon, it's still going to have the same amount of stuff in it. So the mass would be the same if I'm on Earth or if I'm on the moon. The weight would change depending upon where I am in the universe. So that leads us to this next equation. If you're given the mass and you want to find the weight, let's say, for example, I've got a 500 gram mass, okay? Which is going to be 500 grams is the same one no matter where I am. So if I just have this, and I don't have the handy dandy little Newton scale, and I want to figure out how much it weighs, then, and you all did this in the very first lab that you did when we did springs, okay? I'm going to take 0.5 kilograms, I'm going to multiply that by 9.8 meters per second, and I would get 4.90 newtons, okay? So that's your other option, and that's what you've got, that's what you guys have to be able to do in the lab today on your portion dealing with this force table, okay? So you can either take the scale, hang it up, or if you know the mass, multiply that by 9.8 meters per second squared, get the number that way. But this has to be in kilograms, okay? No exceptions, that has to be in kilograms. Not pounds, okay, not ounces, has to be in kilograms. So, here's what your cohorts did on Friday. They were trying to calculate the coefficient of friction of mu. So, there's two types of friction. You have static, which means from rest, and then you have kinetic, which comes from the Greek word kinesis, meaning in motion. Okay? That was horrible. In motion. Okay? So in both of these, one way to calculate mu is that it's force friction over force normal. So what they did is that they took the block of wood and they weighed it. In this case, it was 3.82 newtons, okay? Now, that's my gravitational force. The table is providing an upward force of 3.82 newtons. Now, if you look on your equation sheet, okay? If you look on your equation sheet, you have this, that force normal equals Fg cosine theta. And later on, you'll see where that trig function comes from. So for now, until we get onto inclined planes, you don't have to worry about the cosine theta part of this. And not until like next week, when we get into inclined planes, you have to worry about this. Because it's a flat surface, the cosine of 0 is 1. So your normal force is just going to be the same as your gravitational force. That's it, okay? Fn equals Fg. So in this situation, this is why these two numbers are the same. Now, if you want to, I would recommend making this like your negative value, because that's the gravitational force that's acting down. The normal force in the table was acting up. Now, here's what's important. At this point, when I add a positive 3.82 to a negative 3.82, that's going to add up equal to 0. There's only two possible types of force problems you can have. You either have constant velocity, and all the forces add up equal to 0, or you're accelerating and the forces don't add up equal to 0. That's the only two things that can happen. Constant velocity or accelerated motion. In this situation, the constant velocity would be 0 because it's just sitting there. Now, if we want to calculate mu, did we get a second one? Because they delivered that one right behind you last week. I mean, it's, okay, now we are good for like the next 5 years.
Okay.
Okay, thanks.
Happy visiting.
Okay. Okay. Fish food. Anyway, so everything's going to add up to equal to 0. So if we want to calculate mu, I've got the force normal, that's 3.82 newtons. So I have this number. The tricky part is getting the frictional force. So, and again, I would recommend that you do this just so you get a feel for how this deal works. So I'm going to re-zero the scale because now I'm going to pull it horizontally. So I'm going to hook this up and I'm going to pull it, and it takes, I don't know, 1.11 newtons. Whatever force that takes. And this is going to be important. To pull it at a constant velocity. So if this force applied is 1.11 newtons, that means that frictional force would be negative 1.11 newtons. So one way to determine the amount of frictional force is you measure how much force it takes to pull something at a constant velocity, and whatever force that is balancing out the frictional force. Now, here's the most important thing that you have to keep in mind. The only reason that you have to apply this force is because there's a frictional force in the opposite direction. If you eliminate friction, if you take away all friction, you do not have to keep applying a force to keep something moving, because inertia, which is this tendency to keep moving, you could give this thing a push and then it would just move continuously in a straight line. So like if I take this hockey puck and turn this on, okay, and give that a push with the hovercraft working on it, it doesn't stop. Its inertia is just going to keep it moving. So if you're in deep space, if there's no friction, you don't have to keep applying force. So one of the things I want you to get out of your minds right now is that a force is always necessary to maintain motion. It's not. If you can eliminate friction, which we can't, but if you could, if you're in deep space, which is what we take advantage of, then you don't have to keep applying a force. So if I were to calculate this mu, I would take 1.11 newtons and I would divide that by 3.82 and I'd get probably something around like 0.4, okay, whatever that is. It's just a number. It has no units, it's just a number, okay? Now, if I take and put sandpaper underneath here, I had some sandpaper that I brought up here. There it is. Now, if I put sandpaper down, and then I go to pull it, okay, now that's up to like 3 newtons. So if I'm pulling this thing across sandpaper, instead of 1.11 newtons, that's going to be 3 newtons. Then I'm going to take 3 and divide that by 3.82. mu is going to become a much bigger number. So here's an observation. The bigger mu is, the more frictional force there is. So like if we have like an ice storm, okay? Ice storms are bad because you don't reduce the weight of your car. But what you do decrease is the amount of friction available to stop your car. With a lower amount of friction, you don't have as much force available, you can't stop your car very quickly. And that's why you tend to coast quite a ways on ice, is because of the fact that you have a low amount of friction. Okay? So, here's option number one to calculate, to determine force friction. Figure out how much force it takes to pull it, your frictional force is in the opposite direction. So, if I want to calculate the mu of Ellie, I would put her on the floor, I would take a force meter, I would measure how much force it took to pull her at a constant velocity, I would divide that by her weight, I would have the mu of Ellie. Okay? Now, that's if it's kinetic, pulling at a constant velocity. If you want the coefficient of static friction, you would do that. That's a little bit trickier. You'd sit here and you just pull this until it just begins to move, and then then it's the same calculation. So the only difference is that if it's static, it's how much force it takes to pull it from rest. If it's kinetic, it's how much force it takes to pull it at a constant velocity. That's the only difference. So, what you're going to do, and you can either take the data that they have, or if you have time, if you guys want to collect your own data, you can. So, down here on number 3, where it says draw a free body diagram showing all the forces being pulled at a constant speed. So, what I'm looking for on this, on number 3, you're going to have something like this. You're going to have your Fg, your force normal, your force applied, and your force friction. Assuming that you're going to let 2 centimeters equal 1 Newton, okay? At a minimum, you have to label the forces, because if you don't label what the forces are, it doesn't mean anything. Ideally, you'd also write down the numeric values with it. So you know, oh, here's force friction. You know, negative 1.11 newtons, 1.11 newtons, 3.83 newtons, positive 3.83 newtons. Okay? This is done with a ruler to scale. Okay? So like if that was your scale, 2 centimeters would equal a Newton, you would draw this like 2.22 centimeters long. You would draw this 7.8 or 7.66 newtons long. Okay? Basically, you're going to double the number, and that's how long you're going to draw that. Okay. Now, the next thing you're going to do on number 4, you're going to draw them tip to tail. So on number 4, that diagram is going to look something like this. Fg, force applied, force normal, force friction. And what you should, and again, you're going to use the exact same scale that you drew up here. You're just going to draw them tip to tail. And you're going to end up back at the origin because it was pulled at a constant velocity. All the forces add up equal to 0. Now, here's what I want, the other thing I want to get rid of. This is not Newton's third law, that this applied force here is equal and opposite to that force of friction here. Newton's third law plays out where this here hooks up to that. That's Newton's third law. The earth pulling down on the table, or excuse me, on the block pulling back up on the earth. The block pushing down on the table pushing back up on the block. That's Newton's third law of motion. This is not Newton's third law of motion. That's where you have coupled forces, which we'll spend more time talking about. Okay, so that's what those diagrams are going to look like. When they got down here to number 5, what they did is they began to stack weights on a scale. So like they put like a 500 gram mass, put that on there. If they measured how much force it took to pull it at a constant velocity. You've got those numbers. Now, what they did is that like this block weighed 3.82 newtons. You have a 500 gram mass. This 500 gram mass, like we said, if you multiply that by 9.8 meters per second, you get 4.9 newtons. So the total weight would be 4.9, which is this, plus the weight of the block. Add those together, they figured out how much force it took to pull it at constant velocity. So you just kept adding more and more and more weight. So what you want to do on number 5, okay, you're going to draw a graph, and you're going to put force friction here, and force normal here, and this is like an absolute value kind of thing, okay? They don't make these negative, make this an absolute value. And you're going to plot these points, and then you're going to draw a line of best fit. And emphatically, I tell you in the instructions, I want you to circle the points that you picked that are on the line. You can't use your data points unless your data points happen to be exactly on the line. Okay, that's the whole point of a line of best fit. Go to your graph, circle these. You can show me the slope calculation here. You can show me the slope calculation in the space. I don't care. Show me the slope calculation. But look what you're doing. You're taking force friction and you're dividing it by force normal, otherwise known as the calculation of mu. So the slope of this line gives you mu because you're taking force friction and you're dividing it by force normal. Okay? Now, then play the what if game. Well, if there was less friction, this line would flatten out because it wouldn't take as much force to pull it. If there was more friction, this line would get steeper because it would take more force to pull it. So the slope of this line is reflective of how much force there is available. Okay. So that's through number 5. Now, let's talk about number 7. So on number 7, here's the situation. You've got a carrot car, right? With a mass of 1,000 kilograms, and this thing is moving at 10 meters per second. Okay? So here's what you have to remember. This car doesn't want to stop. This car actually wants to keep moving at 10 meters per second. And the only way that car's velocity is going to change is if a force acts upon it. So if you read what's happening on number 7, we're going to make this car stop because we're going to hit the brakes. Now, I've given you mu. That's 0.700. You know what mu is. So we're kind of flipping the script from what we did at the beginning. In this case, I've given you mu. Now, you want to find the frictional force acting on the car. So if you go up there and you go, oh, force friction equals mu times force normal. Okay, this is an absolute value thing. So I've given you mu. Okay, you know what this number is. You have to calculate the normal force, which is going to be the mass of the car, multiplied by 9.8 meters per second squared. So then you can find this number. So just basically, you're going to take 0.7 times the weight of the car, and that's going to get you your frictional force. Okay? Don't make this complicated. Now, basically what we're trying to do is that on a velocity time graph, we have this car starting at 10 meters per second. Now, when we hit the brakes, this is the velocity time graph. When we hit the brakes, what do we want your velocity time graph to do? Go up, go horizontal, or approach 0? Suzanne?
Go down.
Yeah, that's the whole point of hitting the brakes, right? You want to make your velocity time graph approach 0. So we want this thing to go down like this. Now, here's the $1 million question. I have a positive velocity and I want this thing to stop. Ellie, am I going to have a positive acceleration or a negative acceleration? What'd you say?
Negative.
Yeah, because I have a positive velocity, so I have to end up with a negative acceleration. Now, hanging back there is this big sign that says F equals ma. So, mass is a scalar quantity. It's just a number. It's never negative. So what this means, and this is going to be important, is that my acceleration and my force have to have the same sign. So if I want to, and friction is what's making this car stop, right? So if I want negative acceleration, I have to have a negative force, because your acceleration and your force always have to have the same sign. Okay, there's no exceptions. I can't have a positive force creating a negative acceleration. Okay, it doesn't work. So in this situation, here's what you want to do. This calculation just gives you the force friction. At this point, it's just a number because it's an absolute value. So what you need to decide, do you want your frictional force to be positive or do you want your frictional force to be negative? You have to make that decision. Well, if you have a positive velocity and you want to stop your car, what sign, and Ellie just said, hey, I have to have a negative acceleration. Well, if I have a negative acceleration, I have to have a negative force. So when you get your answer, you just have to make it negative in the context of the problem. Now, if this was a negative velocity and I wanted to stop the car, then I'd have a positive acceleration and a positive force. So one of the things when you get your force friction, you have to decide in the problem, do I want that to be a positive or negative value? Because it's just an absolute value coming out of that. Okay, so the only thing that's going to happen different on number 8 is that I've increased the mu from 0.7 and I've changed it to 1. It's the exact same calculation. Instead of 0.7, I'm going to have this as a value of 1. Now, look at it this way. Okay, so let's say this was the slope when mu equaled 0.7. Now, here's the leap of faith that I want you to take. If I increase the coefficient of friction to 1, okay, Miss Eiston, I'm going to increase the coefficient of friction to 1. Then I'm going to multiply that by force normal. So what's going to happen to my force friction? Will it be bigger or smaller than if mu equals 0.7? Bigger. So I'm going to have a bigger force friction, right? Now, we also said that force friction equals mass times acceleration. So if I have a bigger force, right, what's going to happen to my acceleration? Would it be bigger or smaller? Bigger. So I'm going to have a bigger acceleration, right? So this is where you have to think this through. Okay? Now, okay, I have a bigger mu. I have a bigger force friction. I'm going to have a bigger acceleration. So if this is the line on my velocity time graph as mu is 0.7, is the line when mu equals 1, so is that going to be a steeper line, or is it going to be a more shallow line? Raymond, if mu equals 1 and I have a bigger force and I have a bigger acceleration, is that going to be a steeper line or a more shallow line?
Steeper.
Beautiful, because I'm going to have a bigger acceleration. So if this is 0.7, right, then if I have a bigger coefficient of friction, I'm going to have a steeper line. I'm going to have a bigger acceleration. Look what happens. Remember, what does the area under a velocity time graph give you? Displacement. So if I have a steeper line, my stopping distance is going to be less. This line out here might be happening like if we have an ice storm. So on terms of a velocity time graph, if it's icy or if it's rainy and the roads are slick, your coefficient of friction goes down, your stopping distance increases because you have a smaller acceleration because you have a smaller force. So this is why when it's icy or right after it rains, that's when roads are really slick, is right after it rains, because it's got that slick oil and water combination on it on the roads. You always want to leave more distance in front of you because your velocity time graph is going to be more shallow because you don't have as much friction and you're not going to have as much acceleration. So just graphically, you can look at this and go, wow, that stopping distance there is going to be a lot bigger than that stopping distance here. Okay. On the back side on number 9, okay? On number 9, here's what you want to look at on this one. So one of the things so here's what we've determined so far. One option to calculate my force friction is I pull it. See how much force it takes. The other option is that I multiply mu by force normal to get my force friction. The other thing that I can do is I can use mass times the acceleration that it causes. Okay, so this is going to be the third way that I can do this. So on number 9, and this is why you have to be able to do acceleration before you do forces. So on number 9, you got a car moving at 15 meters per second. It's brought to rest in 20 meters. Determine the acceleration of the car to the frictional force in mu. So on number 9, what variable are you missing in terms of calculating acceleration? Time. So what are you going to use? Which equation are you going to use? You don't have time. What's the only equation that doesn't involve time?
V2 equals V0 plus 2.
Yeah, that equation. V squared equals V naught squared plus 2AD. So on number 9, you're going to calculate the acceleration, okay, using that equation. You're moving with a positive velocity and you're slowing down. So what should the sign of your acceleration be? Positive or negative, Riley? I got a positive velocity. I'm going to try and make it stop.
Negative.
Yeah, I should end up with a negative acceleration, right? Then you're going to use that equation to get your acceleration, and then your force friction, right? So then, once you get your mass and your acceleration, you're just going to multiply those two numbers to get your force friction. Okay, so now you're going to have this number. Then the last thing you want to do is you want to calculate mu. So that's going to be force friction over force normal. So you're going to have this number because you just found it. Your normal force is the same as your weight, which is going to be mg. So you're going to take mass times your gravitational acceleration to get this number. You just found your force friction, so then it's just a matter of dividing this out. Now, this is the classic example where this is like an absolute value. Your frictional force is going to be a negative number. Your normal force is going to be a positive number. But this is an absolute value. So don't even worry about the negative sign up here because mu is just going to be a number. Okay? Okay, when you get to number 10, okay, the two most important words in all of number 10 are constant velocity. So what I'm looking for on number 10 is this. Here's this block of wood, okay, and the block of wood is moving in this direction. So that's in the instructions. I've got an arrow pointing. That's what I'm telling you. So on number 10, because it's a constant velocity, what do I want all of the forces to add up to? 0. So on number 10, when you sketch this, you should have 4 forces. You should have gravity acting down, the normal force, your applied force, and your frictional force. Okay? So on number 10, you're just going to make a sketch. You do not have to draw these to scale. It's just a sketch. The reason that I do that is because if you don't know what forces are acting on an object, you can't figure out how to do the math. So that's why I want you to make that sketch. So if you come into me and you go, hey, Mr. Werkamp, I don't know how to do a problem. Here's the first thing I'm going to ask you. Have you drawn a sketch with all of the forces acting on the system? And if you go, no, I haven't, I will refuse to help you until you do that. Because if you don't know what the forces are and in which direction they're acting, you have no chance at all of solving the problem. Okay? So all I'm forcing you to do is draw this value. So on number 10, I've given you the coefficient of friction. I've given you mu. It's 0.158. So if you can figure out what the frictional force is, then you know what the applied force is. Okay. Now, what the lab that you guys are going to have to do. So give that camera a swirl, Riley, so we can get over here. And then I'll move this one. You move that one.
Hotwood.
Okay. So this is a table, and we use it to study forces, so it's called a force table. Not the most clever marketing technique in the world, but you get the point. So what you're going to do is that the top of this table is laid off like in a 360-degree circle. So what you want to do is change, and you can change two different things for each string. You can change the amount of weight that's hanging down, and then you can also change the angle in terms of where this force is being applied. So what you want to do, through a combination of changing forces and changing angles, you want to get this ring where it stays right. There's a little stop that sticks out, and you want to get that ring where it's right there in the middle. Now, what I don't want you to do is that I don't want the same weight hanging on all three and then all the angles are the same. I want different weights on these, okay? So don't just go, oh, we'll just put a 200-gram mass on each one and boom, we're done, okay? That defeats the whole purpose of this. So if you get this set up, like if you'll notice when I put this ring here, it just stays right there. I've got this whole system in equilibrium. So on your data table, we're going to have three vectors, A, B, and C. So you're going to have vector A. We're going to keep that at 0 degrees. Okay? Then, just like we've done before, so here's 0. We're going to go counterclockwise around like this. So vector B, like in this case for me, would be at 119 degrees. So I'm going to start here at 0. I'm going to go around like this. Here's 119. Then I'm going to go around here to vector C, and in this case that's going to be like 264.5 degrees. So here's 0, here's B, here's C. Got that? That's the easy part. Then, and then, like I said, you can adjust the amount of weights hanging down, things like that. You want to try and get a lot of weight. Just don't have like a couple of little weights hanging on each end. You want to try and get as much weight as you can on this. So after you get done with that, and you get it all set up, and you have your angles, then what you need to do is take these off, and like on each weight, there's a number stamped. So like this is 20 grams. The next one down is like 10 grams. So you're going to take all these weights off, and then you're going to add them all up to get the total amount of mass. These are stamped in grams. Convert them into kilograms, divide by 1,000. So on this column here where it says mass, you're going to fill in that total amount of mass that's hanging on each string. Then you're going to get your FG. So your weight calculation is, you're just going to take whatever that mass is, multiply it by 9.8 meters per second squared. Do not, on this one, make that FG a negative number. The angle is going to tell you which direction this thing is pulling. Okay? So on that number 6, when you're filling in this data table, do not make the FG a negative number. Just get the number, then figure out the angle, because that's going to tell you which direction it's going to act. So what you're going to do after you get that number, so then, we're back. So what you're going to do is that you're going to have up here on number 3, okay, and the equilibrium part, determine the scale and draw the vectors in a free body diagram. So on number 3, you're going to have something like this. You can have vector A. I'd have vector B, which is going to be like 120 degrees, and then I would have vector C. So these are going to be fairly small values because we're not hanging a whole bunch of weight on here. Again, I would choose a scale maybe like 2 centimeters equal Newton. If you have really small numbers, you might even let 3 centimeters equal Newton. So again, this has to be drawn with a ruler you're gonna take a protractor, you're gonna measure this angle, you're gonna measure this angle, you're gonna draw this to scale. I'd write down what these numbers are, okay, because everybody's numbers are gonna be different. You're trying to make this easy for me to grade. You're gonna have A, B, and C. Then on number 4, then you're gonna draw it tip to tail. So on number 4, you can have something like this. You're going to draw A, B, and C. In an ideal world, you would end up back here at the origin. Now, odds are you're probably not going to end up exactly here, but you should end up pretty close. If there's a little bit of a gap, hey, welcome to science. Now, if you draw this and you end up way out here, something's gone horribly wrong. Okay? Something has gone horribly, horribly wrong. So, these are the 2 diagrams that you're going to draw for this one. Free body diagram, tip to tail, use the same scale, measure these angles, draw them with a ruler, make it look nice. Okay? When, on that last question on number 7, here's what I want you to visualize on number 7, is that if you were to draw the resultant of like A and B. So in other words, if you took B and you move that over here, the resultant would be pointing up like this. So if you think about it, this is like a 3-way tug of war. C is balancing out the effect of A and B. A is balancing out the effect of B and C. C is balancing out the effect of the other. So it's like a 3-way tug of war. So if you cut this string, this thing is going to go in this direction. If I cut A, it's going to go in this direction. Okay? So that's what I want you to think of when you go to answer that last question. So, I'm done. You have the rest of the time. This is due tomorrow. If you want some graph paper, I'm going to put a stack of graph paper over there. If you want to use that on your diagrams, you don't have to. I implore you, make sure that I see what the scale is on your diagrams. Make sure that you label the vectors. Not mandatory, but I suggest you write down the numbers so you know what you've got. So what you guys need to do is, there's like, let's have like 2 groups, okay? Set up a force table. There's a whole bunch of them back there. Get the system in equilibrium. Get the data. You don't have to, but I would recommend also, just so you can make sure that you understand how this works. There's all the equipment is still back there for the first part of that lab, where you can get a feel for how static and kinetic friction works. So you just might do that so you get an idea for how that plays out. Okay, I am done. You are on your own. Now hold on. Give me 1 second though. Hold on.